In this video, we're going to take a look at some parametrizations of common curves. And you can think of this video as somewhat of the parametric version of some sort of like design pattern, like you might see in architecture or software engineering, where these are just various ways of making the parametrization process a little bit easier on you using some of these techniques. So first up, if we have y as a function of x, like y equals, let's say, x squared minus 3x plus 1, as x runs through some interval, which we'll call I for interval in this video, then the parameterization is fairly easy if we just let x equals t and substitute that value of t into our function and let t run through that interval. So instead of y equals x squared minus 3x plus 1, it'd be y equals t squared minus 3t plus 1. So fairly simple process for y as a function of x. For inverse style functions, I guess, or for x equals a function of y, pretty much the same thing. We're going to let y equals t and then rewrite our function of y for x using it as x as a function of t. So again, if it's y is a function of x, then let x equal t. If x is a function of y, then let y equals t and substitute that value of t into the original expression. For a directed line segment with initial point x0, y0 and terminal point x1, y1, if we let x equal our initial point plus the difference in x coordinates times t, and then the same thing for y, for values of t between 0 and 1, this will give us our equation, parametric equation for our directed line segment. So a little bit like vectors and such, where we looked at values that would alternate, in this case between 0 and 1, for our difference in x values in front of it and our difference in y values in front of t for our y equals. So just as a way to make it easier on yourself, for directed line segments with initial point x0, y0, and terminal point x1, y1, just have x be the initial point plus the difference in terminal minus initial times t, and same thing for y. And use values of t between 0 and 1. For an ellipse, and bear in mind a circle is just a special case of an ellipse, in the form x minus h, our standard form for an ellipse, if we let x equals h plus a cosine t and y equals k plus a sine t, and we can let t go between 0 and 2 pi. So we saw this at the end of the last video with the 3/4 ellipse that we had. If we had gone the entire rotation to 2 pi, it would have fulfilled the rest of that ellipse in the graph. So example 4, parameterization for each of the following. We have y equals x squared from -3 to 2. So we have y as a function of x. Well, just let x equal t, and then y will be t squared when t goes between -3 and 2. For part B, we have y is the inverse of x, where f of x is x to the 5th plus 2x plus 1. And we got y equals x to the 5th plus 2x plus 1. And that means x equals y to the 5th plus 2y plus 1. So switching the x and y when finding our inverse. And now we have x is a function of y, so let y equal t, and then x will equal t to the 5th plus 2t plus 1 for all possible values of t. We have in example 4c, the line segment with initial point 2, -3 and terminal point at 1, 5. So going back to that third bullet point from before, our difference in x coordinates, 1 minus 2 is -1. Our difference in, so x is going to be our initial point of 2 minus 1 times t. So 2 plus -1 times t is 2 minus t. y1 minus y0, 5 minus -3 is 8. So y is going to be our initial point, our initial y coordinate, plus 8 times t, which is -3 plus 8 times t. So again, directed line segments, a lot, pretty much vectors. That's exactly what they are. They're vectors. They're directed line segments. And again, we're going to look at values of t for this x and this y between 0 and 1. Example 4, the circle, x squared plus 2x plus y squared minus 4y equals 4. Here we have in an ellipse style form, x plus 1 squared over 9 plus y minus 2 squared over 9 equals 1, much like we did with ellipses, going from this form given to standard form. So with x, it's h plus a times cosine t, so h is negative 1 plus 3 cosine t. Y is going to be k plus b sine t, so 2 plus 3 sine times t, for values of t between 0 and 2 pi. All right, example 4, part E, the left half of the ellipse, x squared over 4 plus, that should be y squared over 9 equals 1. So we're going to let x equals 2 cosine t, so we have x minus 0, so 0 plus a squared is 4, so a is 2. Y will be 3 sine t, and because we're looking at the left half of the ellipse, we're going to consider values between 90 and 270, or pi over 2 and 3 pi over 2. So if we look at the y-axis as pi over 2 on top and 3 pi over 2 on the bottom, anything between pi over 2 and 3 pi over 2, between 90 and 270 degrees, will give us the left half of that ellipse. If we wanted the right half, we could do something like negative pi over 2 to positive pi over 2 to get the right half of the ellipse. All right, that about does it for this video. Thank you for watching, and I'll see you next time.